Today I'm going to be explaining trig subs, which is another strategy for integration. So trig subs are particularly useful when we have to integrate one of these three sort of functions, where a is a constant. So if we have to integrate one of these three sort of functions, we use the following substitutions for x and then the following trig identities to solve for the integral. So let's just start off with a couple practice problems. We have the integral of 1 over the square root of x squared plus 25. We know we can use a trig substitution of tangent to solve this integral because it is in the form of x squared plus a squared, where a will equal 5. So that means our x will equal 5 tangent theta for our substitution. And that means our dx will equal 5 secant squared theta d theta. So using these substitutions for x and dx, we get this thing right here. And now we can pull out a 25 from the radical, and our 5's will cancel out. And then we have to use a trig identity formula. We know that tangent squared theta plus 1 will equal secant squared theta. That means a secant will cancel out from the top and bottom, and we're left with the integral of secant theta d theta, which is equal to the natural log of the absolute value of secant theta plus tangent theta plus c. Now, to simplify this even further, we need to get our thetas in terms of x's because our original integral was given in terms of x's. So we go back to our original substitution to isolate theta. And by the original substitution, we know that theta will equal arctangent of x over 5. Now we substitute our theta value for this entire thing. And then we're ending up with this entire thing right here. And to simplify even further, we can draw a triangle knowing the fact that tangent theta will equal x over 5, meaning the opposite side of theta will equal x and the adjacent side will equal 5. Now we can use Pythagorean's theorem to solve for the hypotenuse, which will be the square root of x squared plus 25. Now we substitute in all these values using the three values of the triangle to get our final answer right here. Let's do a second example problem. The integral of the square root of 6x minus x squared minus 5. Now this will not be obvious to us right away to use a trig substitution because it is not in one of the three forms that we know. So we have to complete the square to try to get it into a form that we can use a trig substitution for. So completing the square, I pulled out a negative sign from the first two terms to get x squared to be positive, and then I added 9 to the outside and added 9 inside. And technically, it's subtracting 9 because we took out a negative from the first two terms. Now, after we complete the square and simplify a bit, we get the integral of the square root of 4 minus x minus 3 squared. Now, I pulled out a 4 from both of these terms to get this right here. And we can also pull out a 4 from the radical, and we have now 2 on the outside of the integral. And then we also know that x minus 3 squared over 4 is equivalent to x minus 3 over 2, all of that squared. So we rewrote that here. And now this can be easily seen and use a trig identity or trig integral or a trig substitution for sine. So x minus 3 over 2 will equal sine theta, meaning dx will equal 2 cosine theta d theta. So we make our substitutions for x and dx, or x minus 3 over 2 and dx, and then we get this. We simplify a bit further, and we end up with the integral 4 times cosine squared theta d theta. Now we have to use a power reducing formula. We use a power reducing formula here. We simplify a bit further. We end up with 2 theta plus sine 2 theta plus c. And for sine 2 theta, we must use a double angle formula. So we rewrite it like so. 2 theta plus 2 sine theta times cosine theta plus c. Now, just like the last problem, we need to isolate theta from our original substitution. We get theta equals arc sine of x minus 3 over 2. And then we substitute our theta values for this value right here. We get this giant thing. And then now we can simplify even further using a triangle. We know that the opposite value will be x minus 3 and the hypotenuse will be 2. Using Pythagorean's theorem, we can solve for the adjacent value, which will end up being the square root of 6x minus x squared minus 5. So simplifying with this triangle with these three values we know, we get the final answer here of 2 times arc sine of x minus 3 over 2 plus x minus 3 times the square root of 6x minus x squared minus 5 all over 2 plus c. Now let's do a third example problem. We have the integral of 1 over x to the 4th power times the square root of x squared minus 7. We can use a secant substitution because it is in the form of x squared minus a squared. So that means our substitution will be x equals root 7 times secant theta, meaning that dx will equal root 7 times secant theta tangent theta d theta. We make both our substitutions for x and dx, and we get this giant thing right here. We can pull out a root 7, and our root 7s will cancel out, and then we can use an identity because we know that secant squared theta minus 1 will equal tangent squared theta. Then our tangents cross out, and one of our secants cross out. Then we end up with the integral of 1 over 49 times 1 over secant cubed theta, which is equivalent to 1 over 49 times the integral of cosine cubed theta. Now, to solve this integral, we use another technique, and we can split this cosine cubed theta into cosine squared theta times cosine theta. Then we can use another identity. We know that 1 minus sine squared theta equals cosine squared theta. And then we can use a simple u substitution for this, having u equal sine theta and du equal cosine theta, which will solve nicely using a u substitution. And then we will end up with this right here after subbing back in the u value. All right, once we get to this point, we go back to our original substitution, which was x equals root 7 times secant theta. We isolate theta once again. Our theta will equal arc secant of x over root 7. And then we substitute our theta value, and then we draw a triangle once more, and we solve for the missing value. And this missing value will be the opposite side, and we end up getting the opposite side will equal root of x squared minus 7. And then we will substitute all our values to get our final answer right here. Now for our final problem, it will be a definite integral from 1 to root 3 of the square root of 1 plus x squared all over x squared. So we can do a tangent substitution because it is in the form of a squared plus x squared. So we'll set x equal to tangent theta and dx equals will equal secant squared theta d theta. So we switch the bounds right away to not get confused. We know that using this right here, 1 will equal x, 1 equals tangent theta. That means theta will equal pi over 4. Root 3 equals tangent theta. That means theta will equal pi over 3. So we switch the boundaries right away. And now we can make our substitution of x and dx. We get this all right here. Then we use another trig identity like we did before. We know that 1 plus tangent squared theta equals secant squared theta, and that's under the root. So we get secant theta over tangent squared theta times secant squared theta, which we now have to use another identity to solve this problem. This is what makes this problem so difficult, is to realize we need to know when to use these identities and to use them well, so to make the integration problem way easier. So we know that secant squared theta will equal 1 plus tangent squared theta. Then we distribute the secant theta to each of these values. And then we end up with this right here. We can cross out our tangent thetas. And then we can solve or rewrite this expression right here to have it be like this, plus secant theta after crossing out the tangents. And then we simplify a bit further. We get the integral from pi over 4 to pi over 3 of cosecant theta cotangent theta plus secant theta d theta. We know the integral of cosecant theta cotangent theta will equal negative cosecant theta. And then we know that the integral of secant theta is a natural log of the absolute value of secant theta plus tangent theta. And we're solving this from the interval of pi over 4 to pi over 3. And using simple arithmetic and trig, we get the final answer of root 2 minus 2 times root 3 over 3 plus natural log of 2 plus root 3 minus natural log of root 2 plus 1. So some common mistakes for trig substitution is overusing trig subs. Many times when we have a complicated looking integral, most people usually just get mixed up and use trig sub right away, when usually a u sub will take care of it much faster. On an AP exam, you will likely be time limited and time pressed, so you want to use the most efficient method for integration. Another common mistake is setting x equal to cosine theta, which is not one of our three forms. Our three forms is x equal a secant theta, a tangent theta, and a sine theta. Cosine theta is not one of them. Another common mistake is not knowing when to complete the square. This can be very tricky, but you just have to get used to it and do some more practice problems and you'll get the hang of it. Plus C's is something always to remember for indefinite integrals, and then not switching boundaries for definite integrals is a common mistake.